In this video, we're going to be talking about springs and deformation, and we're going to start with a general definition that describes what deformation is. So, deformation. You can think of deformation as just something that changes its shape or size. Like, imagine if you have a rubber band. If you stretch it, it's being deformed. If you squish it, it's being deformed. That applies for everything, but just on smaller scales. So say you have a Mars bar, you squash it, it's getting deformed, it's changing shape. If you have a pen and you stretch it, it's getting deformed, it's changing shape. So we can write that deformation is when a material changes its shape or size. Now that we have a general definition for deformation, we need to know the different types, and there's two. So there's compressive deformation, and you can think of compressive deformation as what I've done to the Mars bar. So as you can imagine, compression, it gets compressed and it changes shape. So I can just draw a picture of that. So if there's an object, a material, and then there's a force acting on it which causes it to compress. Then the other one that we need to know is tensile deformation. And this is kind of the opposite of compressive. So if you imagine compression to be pushing something together, tensile is going to be pulling it apart. So I can just draw that as well. Now we need to know about Hooke's law. And all that says is that when you apply a force to a material, it can stretch up to a certain point, and up to that point, the force is directly proportional to the extension. I'm writing this in a mathematical term. It will be F is directly proportional to extension. And then to write it in an equation, we'll say that F equals Kx, where K is some spring constant. So, now to define what a spring constant is, because that's quite an abstract phrase. So, spring constant. The spring constant is the force that's needed to extend an object by 1 meter. Now, let me just draw a quick demonstration. So say we have a platform with a spring hanging down off of it, and attached to that spring there's some mass which exerts a downward force. So we would say that this extension follows the relationship F is equal to Kx. So if we have this diagram here, there's a mass on the end of a spring which is attached to a platform, and the force pulling it down, because it has mass, is going to be proportional to the extension. Now if we have a platform and we have two springs connected to it, and then there's a mass acting on this as well, so that's exerting a downward force, and this is spring 1 and this is spring 2, then to add the spring constants together, if they're in parallel, so in parallel, K is going to be equal to K1 plus K2. Simple enough. So when they're together, if say this spring constant is 60, this one is 70, together they're going to be, the total spring constant is going to be 130. Now, if we've got a similar situation where we've got a spring hanging from a platform and then another spring with it, but this time it's not going to be in parallel, it's going to be in series. So we have two springs, this is spring 1, this is spring 2. We can say that the spring 1 divided by the spring constant, the total spring constant, is going to be equal to 1 divided by the spring constant of the first spring plus 1 divided by the spring constant of the second spring. And then we can just make it a bit easier, just have K by itself. K is equal to, open brackets, 1 over K1 plus 1 over K2, close brackets, to the negative 1. Now to talk about that limit, that proportionality limit. So if we draw an axis where on the y-axis we have force, and on the x-axis we have extension, then we're going to see a general shape like this. So notice from 0 to somewhere about here, this here obeys Hooke's law because f is directionally proportional to x. So you can see that it's linear, so obviously they're the same and they pass through the origin. But once we get to this point here, this is something that we can call point P, and that's called the proportionality limit, or limit of proportionality. And after this point, the force is no longer directly proportional to the extension. So after point P, Hooke's law is not obeyed. We also need to know about another point in the graph called elastic limit. So a little bit after the limit of proportionality, we're going to have the elastic limit. And what the elastic limit says is that once a force exceeds the elastic limit, the object is going to be permanently deformed. So back to the Mars bar example, if I have this and I'm pushing down on it, up to a certain point, whenever I let go, it's going to go back to its original shape. But the second I add too much force, it goes past the elastic limit and now it's permanently deformed and it won't ever go back to its normal shape. So that's basically what the elastic limit is. So let me just write that down. When force exceeds the elastic limit, its shape is permanently deformed. However, if you apply a force to something or stretch something and it reaches before the elastic limit, even past the limit of proportionality, unless it passes the elastic limit, it's going to go back to its original shape. So if the force applied does not exceed the elastic limit, when force is relieved, the material will go back to its original shape. And we can write as well that P, point P, the limit of proportionality, that's the point, if we was to define point P, we would say the point beyond which force is no longer proportional to the extension and Hooke's law is no longer obeyed. So now, under these two types of deformation, there's another set of two types of deformation, which is called elastic deformation and plastic deformation. So elastic deformation, you can think of as you can stretch it, and then as soon as you let go of the force, it will go back to its original size. Plastic deformation is, imagine I stretch it and stretch it and stretch it, and then when I let go, it just stays like this. It doesn't ever go back to its original size. So hence, plastic, if you get a piece of plastic and you pull it, then it's going to stretch out. But if you get something elastic, when you let go, it's going to go back to its original shape. So we can write that down. So we have elastic deformation. So up to the elastic limit, the material will go back to its original shape, hence it's elastic. I find it useful to imagine an elastic band. If you pull it and you let go, it's elastic. It's going to go back to its normal shape. So plastic deformation, if you apply a force that exceeds the elastic limit, the material will be permanently deformed. Now, the last thing that we need to know about this is if we draw another diagram of the same graph, the work done of deforming the material is going to be equal to the area under the graph. So let's say we want to take the work done up to the elastic limit. We would simply find, up to the proportionality limit. So this here is point P. To find the work done, is equal to the area under the graph. So obviously up to point P, this is going to be linear. So up to P, the area under here is just going to be equal to 1/2 force multiplied by the extension. Because you can think of this as a triangle. The area of a triangle is half base times height. So half force times extension. And this is going to be the work done in deforming the material.